skills.
Thank you. So I'm delighted that there were some initial discussions regarding that number. I'm happy to report that. So what I'm going to be talking about today is, using the scalar dissipation rate is related to the gradient of the process period or gradient of temperature. Using that information, how we can model the previous flames, turbine previous flames. Before we say anything on that, I would like to acknowledge my colleagues, Professor Ken Bray and Professor Kaminsky in chemical engineering. He has helped me with some experiments which I'm going to be showing today in the next few slides. And he is my colleague in Liverpool. He does some DNS for me. We collaborate on various aspects of this topic. And Tanahashi in Tokyo Tech, he has done a very big DNS data which I'm using to extract insight into these kind of problems. And these are some of my PhD students who have been working on this topic, as well as working on this topic. And some of these are my postdocs who has helped me to understand this problem more closely. So without acknowledging them, it will be a fair talk. The funding for this work comes from EPSRC and EEC and some of these industrial contacts. As you may see in this presentation, there are some fundamental aspects of this problem which are supported by these funding bodies, and there are also some applied nature of this problem which are supported by these industries. So the objective, I have three objectives today to do in this talk. One is to understand the heat release effect on the small scale mixing and the coupling. Why we are interested in this problem is, let's look at the results in the literature. For example, the turbulent burning velocity or the turbulent flame speed versus the U prime over SL. This is the RMS of the turbulence level divided by the laminar flame speed. This is the turbulent flame speed divided by the laminar flame speed. The points are the experimental data collated by Derek Bradley in 1986, which was published in Proceedings of Royal Society. And these lines are the various models, as you can see here. So I agree there are a lot of scatter in the data, so we can as well throw out the data, or we can take them. That's the best people can do at that time. And the scatter in this quantity is improving as more sophisticated experimental techniques are becoming available. But the interesting point here is these various models, you could see the range of the predictions. So either you could say all of these models are equally good, or all of them are equally bad. Which one is true? We'll find out. So once we develop some understanding of this small scale mixing, then can we develop a simple model to improve, to make a better model predictions, or to develop better or improved models for the turbulent premixed combustion. And then we shouldn't be stopping there. We should also apply them to test whether it can do a better job in predicting the practical flames or laboratory scale flames. So my aim is to have a single model to predict a range of or various phases of the problem, including the flame speed, flame structure, and combustion noise, and whatnot as it comes out. So what I mean by same model means you're not going to tune the model parameters. Given model with the same model parameters, you're going to apply it to predict these various different phases of the problem.
But when you say combustion noise, what do you mean?
You have a flame,
Flame?
and you put a microphone for field.
So it's a real noise.
It's a real noise, yeah.
Sound in some sense, random sound.
Yeah. So the sound generated by the flame. So, but for today, I'm going to be concentrating on these two because these are very in nature of very wide range of topics. So I'm going to be concentrating only on the flame speed and flame structure. If any of you are interested in other topics, I'd be happy to discuss and analysis. So the outline of my talk today, I will discuss what small-scale mixing or the scalar dissipation rate means. I do not have to dwell on that for a very long time because the audience here knows very well what that means and why is it important and how is it important for premixed, partially premixed combustion. Partially premixed is more relevant for a practical application because none of the practical combustion is either premixed or non-premixed. Most of the time we have partially premixed combustion. And my aim is to understand the physics and develop simple models for that. And the development of the physics or understanding of the physics comes from the DNS as well as laser diagnostic data using PIV or sophisticated laser diagnostic data. And then I will also explain how the combustion modeling is done using these information we are going to extract from the DNS. And then we apply this combustion modeling to calculate some of the turbulent Phoenix planes. Not only one, few. So the small scale mixing, what is small scale mixing? Is the scalar dissipation rate. If we approximate the flame to be of that corrugated shape like that, how we can see that is, for example, let's look at a simple DNS flame there. This is a lifted hydrogen flame calculated in JAXA for a H2 air flame. And then if you take a cut there, and then probably if you see from the top view, then you will see these contours which is going to go along on the plane. And that is the contour which is represented.
What's the typical temperature in these situations?
Typical temperature of what?
Well, no, of this flame.
1800 Kelvin, 1800 to 2200 Kelvin, depending on the equivalence ratio. So this is the flame contour, and then when we have a turbulence, the turbulent large-scale turbulence are going to contort the flame and then into the flame, as you can see there. Okay, and then in addition to that wrinkling, if we want to sustain combustion, what we need to do, although the reactants are pre-mixed here, we need to mix the cold reactants with the hot product. If you're not mixing it, if the turbulence is not mixing it, then there will not be combustion. Combustion will not sustain on the flame surface. Okay? That's a very important physical process which is done by the turbulence itself. We are not doing anything extra by the fluid mechanics. So that mixing rate between the hot product and the cold reactant are related to the gradient information which are generated at the flame surface. Okay? And that's the square of the magnitude of the gradient is called the scalar dissipation rate, or the instantaneous scalar dissipation rate after you multiply with the diffusivity of the scalar which you are interested in. For example, if you use Y, if you replace the scalar Y with temperature, then the alpha is the thermal diffusivity. If you use a concentration, then it could be a mass diffusivity. Okay? So this is an instantaneous scalar dissipation rate. That's which is typically called as a small scale mixing in turbulent temperature.
So there is a threshold in the value of gradient of temperature in order to have flame?
That's right. That's what the laminar flame will tell you. If you do a laminar flame calculation, the peak reaction rate will occur at a particular value of this quantity. That's right. So how is it linked to the combustion process? Again, look at the literature from 1975 to probably 2009. Various approaches you could see. I'm not going to go into each of these. The main point which I'm trying to keep here is the scalar dissipation rate appears for non-premixed flame as well as premixed flame. These are for the instantaneous reaction rates. Even if you look at the mean reaction rate, then some averaged form of the scalar dissipation appears in the mean reaction rate as well. Even if you use the FST approach, which was discussed on Monday by Jim in his talk, the sigma is the flame surface density, that is a flame surface area per unit volume. Even if you use that approach, then the mean reaction rate is related to that, and the flame surface density can be easily shown to be related to this scalar dissipation rate, because it's a flame surface density, something but flame surface area per unit volume, that's related to the gradient information. Okay?
And sigma, is it surface or some? What is it?
Surface density.
Surface density.
So it's a surface area per unit volume, which can be shown very well, very easily that it's related to the gradient information, which was shown by Batchelor in 1952 in one of his papers in Proceedings of Electricity. And even if you use this modern approach, CMC, conditional moment closure approach, or joint PDF approach, where you have a PDF transported in the flow, the scalar dissipation rate is going to pop up again and again. So we are not going to be escaping that issue. That's a fundamental issue, we need to address it. So the takeaway from this slide is, if you know a model for the scalar dissipation rate, if you can understand the process of the physical process of the scalar dissipation rate and then develop a simple model for it, that means we know how to close the mean reaction rate, then we can go ahead and do the industrial calculation or a practical flame calculation. That's the idea.
And what does it CM?
CM is a model parameter which was very well accepted to be 0.7.
You use some kind of progressive variable.
This is not a progress variable, C is a progress variable, and CM is a model parameter.
Model parameter.
0.7, which was very well established by various people around the world. So that means if we have a model for this this quantity, that's the scalar dissipation rate, then we can close that mean reaction rate. And Brent Spalding wrote this type of expression in 60s. Then that was based on a chronological idea. Then Ken Brave wrote it in this specific form in a very rigorous manner after using the transport equations and then manipulating the transport.
So SDR means
Scalar dissipation rate. Yeah. That is, specifically I'm talking about this epsilon sub c, which is nothing but diffusivity times del c dot with del c. C could be a normalized temperature or normalized mass fraction.
Swami, can I ask you a question? Scalar dissipation rate occurs in both flamelet and non-flamelet, right? Because if it's a perfect flamelet, laminar mixing only, you still have a gradient of water, right? So small scale mixing though only occurs in non-flamelet, is that correct?
Small scale mixing can also occur in flamelets because strictly this is related to the fluctuating C.
Okay, but if it's flamelet and it's not extinguished,
Yeah.
then there's no way for
The
reactant.
flamelet can create a fluctuation
I guess I'm trying to understand this.
from the turbulence.
But you never have reactants mixing with products if you have a
As,
connected flamelet.
as soon as it mixes, it burns. If they don't mix, then you can't have a burning happening because of this. The radius temperature difference, yeah. So you have to rise the temperature of the cold reactant to a certain level.
I don't think you can have small scale mixing if you have pure laminar flamelets.
I think you will. So you have a laminar flamelets, not laminar flamelets.
Yeah.
Okay. So this is a turbulent flame where you have reactant this side and then product this side.
Yeah.
Okay. And then if you want to mix these two things, then this is at one instant. At another instant, it may be like that. At another instant, it could be like that. So that means there is going to be a C fluctuation in there. The fluctuation of the temperature field or the reactive.
Okay. I guess when I say mixing, I'm talking about a little different mix. You're talking about at a given point,
Yeah.
the mixture changes from time to time. You call that mixing.
Yeah.
When I say mixing, I mean reactants on one side of a laminar flamelet, products on the other side of a laminar flamelet. Those two cannot mix because there's a flame in between. But
In a laminar flame, yeah. In a laminar flame. it
We're
cannot
talking about
mix.
two. Okay,
Yeah.
now I understand.
Yeah.
Okay.
Just for corrugated region of combustion, not for general cable.
No, I understand.
Is it average? Average result or just not exactly?
This is for the average result. The exact result can also be seen in that paper, in this paper. In these two papers, you can see even for the exact, the instantaneous quantity.
Can I also ask a question?
Yeah.
Scalar dissipation rate, in your case, seems related to reaction also.
Exactly, yeah.
In non-premix flame, the scalar dissipation rate when you fuel air mixing.
In non-premix flame, the scalar dissipation rate is,
It's a mixture fraction.
that's right, diffusivity times mixture fraction fluctuation. And this is a passive scalar, which does not have any chemical reactions in it.
So here, this concept is quite fundamentally different
Exactly,
between
yeah.
these two.
Yeah, these two quantities are not the same quantities, they are fundamentally different quantities. This one is only influenced by the turbulent process. And this one is influenced not only by turbulence, and also by chemical reaction. So this,
Isn't it better to call something else? Scalar dissipation.
they can invent a term, yeah, but I'm just using the standard term, so I don't want to create another confusion.
And alpha depends on kinematic viscosity or not?
Alpha is the thermal diffusivity, molecular thermal diffusivity, for this scalar. Okay? So the standard practice, if you look at the literature again, there's a lot of literature, a lot of work, modeling work with physical analysis of this problem in the literature. If you look at it, the standard practice, what people do is they take the scalar dissipation rate and then relate to the large scale time scale of the turbulence. K is the turbulent kinetic energy, epsilon is the turbulent dissipation rate, kinetic energy dissipation rate, and then multiply it by the variance. CD is a model parameter, typically about 1.8 to 2. That works for the passive scalar. But
Tau
if you have a,
approximation. Tau approximation.
yes. And if you have a reactive scalar, then CD can go from 1.8 to 20. Okay? So which value you use, that comes into problem. So what we have done a couple of years back, a few years back, is we wrote a transport equation for the scalar dissipation rate n. N is not this one. N is the instantaneous quantity, alpha times del C dotted with del C. So we wrote a transport equation. This is the exact equation but unclosed equation. So n is the instantaneous scalar dissipation rate, which has got the substantial derivative on the left-hand side, and there's some diffusion term, some dissipation of this n, and then the contributions from the chemical reactions, and the contributions from the turbulence processes, and then this is the contribution from the heat release. As you can see, del dot U is not zero in planes.
Similar to epsilon equation in K epsilon.
Epsilon equation is a phenomenological equation, it's not derived.
Yeah.
Yeah, this is.
This is derived. This is
you mean,
derived.
it's a
Yeah.
bit so.
Why you include alpha in this equation? Because
Why do we include alpha in this equation, in this here?
yeah, I understand. Because usually people write equation for the gradient c squared.
That's right.
Yeah.
But what physically meaningful for combustion problem is this quantity.
Yeah, I
This is
understand.
related to the time scale.
Yeah.
Okay.
Okay. But this is non-universal quantity because it depends on correlation time.
Correlation of what?
Correlation time of velocity. You understand? This is
That is true in the passive scalar situation.
yes.
Once you have the reactive scalar, then the chemical reactions will change, completely change. You will see that in a minute.
But you write evolutionary equation
Yeah.
for the quantity which includes molecular dissipation,
That's right.
which is not universal.
Plus, we don't dispute this equation, do we? We don't dispute that. Yeah? So all you do is you take the gradient of this equation and then multiply that resulting equation with alpha times del C dotted with this guy. That will lead you to that. Directly will lead you to
Yeah, I
that.
understand. Alpha is constant or depends on temperature.
It can depend on temperature.
Okay.
Okay? It can depend. Yeah. It can depend on temperature. While writing this equation, we did not make any of that simplification. We treated alpha to be depending on temperature. It can vary spatially also. That means your time scale can also vary from inside the flame, inside the flow. And this equation was written sometime, not in this form. This similar equation was written by Lumley in Cornell in late 60s or early 80s, and that equation is for the passive scalar, which did not have the contributions from the chemical reactions and which did not have this dilatation term anymore in there. So the French group, Vargy, he borrowed that equation and then started using it for combustion problem in early 90s. Okay? And the original contribution in this work is the identification of the dilatation process on this time scale itself. So how that has come about is we have allowed the density to vary across the plane. So when there is a density variation across the plane, then which is related to the dilatation, which will come out.
And Lumley also include alpha coefficient in this
That's right, yeah.
equation?
That's right.
Really?
Yeah. Because he was looking at the buoyant flow, turbulent buoyant flow, and then he was trying to put it. So if between these two quantities, okay, the passive quantities and the reactive quantity, the counterpart is these two quantities will not appear, these two terms will not appear, and this will be a common term. That's the effect of the turbulence which is coming on this scalar. So that's what we are interested in. The question we are asking is this term behaves in the same way or not? The exact form of that equation, of that term, of the turbulent contribution term is, as you have seen here, which is EAJ is the turbulent strain rate part, and these two are the two different gradients in two different directions, gradient of the scalar in two different directions. So basically this is the inner product between the grad C and the strain rate, turbulent strain rate tensor. Okay? So then you can decompose that using eigen decomposition in this form in a very simple, it comes out to be in a very simple manner. Okay? Where alpha, beta, and gamma are the principal components of this strain rate tensor, and then theta, alpha, theta, beta, theta, gamma are the orientation of this gradient vector with the principal direction.
And this equation has a divergent term. Divergence of third nonlinear term.
Yeah, this is a substantial derivative.
But it's u nabla n. Yeah?
U.
This term is
That term is rho dn by dt
yes.
plus rho u nabla n.
Yes. Exactly. I speak about the term divergence of the nonlinear terms. It should be in this equation.
Which goes into this one. When you derive it, you will see that.
Only here.
Yeah. And you don't have the contribution from the rotation also because you are multiplying by the gradient. So only the strain part contributes to this evolution equation. So what we are seeing here, can I go on?
Yeah.
So what we are seeing here is the contribution from the principal components of the strain rate and its relative orientation with respect to the principal strain rate. Okay? That has been very well studied for the passive scalar mixing from 60s by George Batchelor and in UCSD, probably some of them in Russian also. I don't know the Russian literature well enough. So what they have found is, we will see it in a minute. So what we are after is, we are trying to analyze this term because it appears for the passive scalar as well as for the reactive scalar, and we want to see how this term behaves when there is a chemical reaction in the flow also. Why it is important is because this term is identified to be a very important term for this time scale, even for passive scalar situation. So how we are going to study that is by using the DNS data. This is not only one DNS data we are studying. We are studying many different data sets, as you can see there, and each one of them have a different parameters. So it covers a wide range of combustion conditions. So if you are finding something common among these data sets, that means it has to be true in combustion flame itself, in premixed combustion. That's the point which I'm trying to get across. Okay. So these data sets are generated in different phases. The typical configuration for this DNS is a box turbulence where there is a premixed flame moving from this end to the other end. The cold reactants are flowing this way and hot products are flowing this way. Okay. And in addition to that, if you talk to an experimentalist, he can always query what we are learning from this DNS, because DNS is in a very small size and a very limited range of parameters. And is it going to occur in experiment also or not? So to answer that question,
Yes, you raise turbulent Reynolds number. What is it? It's which based on the energy contained scale, or
that's right. It's based on the energy contained scale. U prime lambda over nu on this side, on the core side.
Lambda you mean
Lambda is a no. Capital lambda. Capital lambda. Okay. So to have more confidence in our learning, we also did some experiments. The experimental burner is like this, very simple burner, where you have premixed reactants going up, and the flames are stabilized here. There is a bluff body there, and then we do OH pliff, and then stereoscopic PAV. OH pliff will identify the flame contour or the flame surface, okay, and the stereoscopic PAV will give the velocity vectors. Although it gives 3 velocity components, we have only 2 derivatives because it's a projected domain. So we have enough information to construct that quantity which we saw a couple of slides earlier, which is the turbulent scalar interaction quantity. So if you analyze these DNS data and the experimental data very carefully, then what we found is, I will tell you in the next slide. Before that, these are the DNS data in the combustion regime diagram, and this is the experimental data. So we are not studying only one regime, the corrugated flameless regime. We are studying a wide range of conditions of the flame. Okay? And the Damphler number is the ratio between the fluid mechanical time scale to the chemical time scale. And the Reynolds and turbulence Reynolds number is defined exactly based on the energy scale. And the Karlovich number is the ratio of the chemical time scale to the Kolmogorov time scale. So basically this number compares the large eddy, the time scale of the large eddy to the chemical time scale, and this number compares the time scale of the small eddies to the chemical time scale. Okay?
The ratio should be depends on Reynolds number.
Of course, yes. The ratio depends on the Reynolds number. In this regime diagram, the constant Reynolds number lines goes in that way, and the Damphler number equal to 1 line is in that line, along that line, and this is a Ka equal to 1 line, the Karlovich number equal to 1, and this is Ka equal to 1. And this is, I borrowed this diagram from Norbert Peter's book. And Ka equal to 1 line is of significance. What that means is your chemical time scale is of the order of the Kolmogorov time scale. Okay, that's what it means.
I'd like to say that this equation for N contains two quantities. One is a C square, another is turbulent time. So in some sense, this equation is not closed.
Yeah, I made that same
Yeah. For example, if you, in addition to this equation, write the equation for the gradient C square, which has a form of conserved quantity, in some sense, which has time derivative, divergence of nonlinear terms, and there is a source term, and dissipation. So these couple equations is enough in order to describe all situations. In the sense, otherwise N contains turbulence time. You don't know turbulence time.
That's what we are trying to predict. I agree, we do not know the turbulent time scale.
Yeah.
That's what we are after. That's what we want to know.
Yes, but if you will use two coupled equations, you have all information from the system.
We'll discuss that.
Yeah.
So this is of some significance, very good significance, not some very good significance here. K equal to 1 line means, the Kolmogorov time scale is same order as the chemical time scale. And below that line, we have a very thin interface. The flame can be treated as a very thin interface, which is called the flame combustion regime. Beyond that line, the small scale eddies can enter into the flame and then disturb the preheat zone or the thermal diffusion zone. But still, the regions where the chemical activities are occurring are intact. That's called the thin reaction zones regime. Okay. So we have explored a wide range of conditions in the wide range of flame conditions. And what we have learned, just to remind ourselves, I have written here again, the turbulence time is written in this way. Alpha, beta, gamma are the principal strain rates, and these are the directions of the principal strain rate with respect to the gradient vector. So what we know from the literature or the classical picture for the cold flow is this, the PDF, what I have plotted is the PDF of this cosine of the angle for these. What I have here is for these two quantities, for the alpha strain rate, which is the most extensive strain rate, and gamma, which is the most compressive strain rate. Okay, if you look at the classical picture, then what it says is the isoscalar surface or the normal of the isoscalar vector aligns with the most compressive strain rate. That's a very classical picture, very well known for many, many years, and it's been proven by DNS experiments and theoretical analysis. If we construct the same quantities from the flame, then completely opposite things happen here. The most probable alignment is with the extensive strain rate, okay? But in classical picture, the most probable alignment is with the compressive strain. Okay? The physical picture behind this is completely different. In classical turbulence, if you have isoscalar surfaces, they are being pushed together. That means the gradient is going to be increasing. And then if you apply a simple molecular fixed law, for the molecular flux, it's going to increase because the gradient is increasing. But in flame, it's aligning to the most extensive strain. That means the isoscalar surfaces are being pulled apart by the turbulence. So instead of generating gradients, the turbulence is destroying, is killing the gradient generation chemical, which was published in those papers.
But you're assuming that the flame somehow, from one experiment, is this is a general result?
This is not one experiment. We conducted 3 different experiments,
Okay.
and 4 or 5, probably 7 DNS data sets for different flame conditions,
Okay.
as you have seen. Yeah.
If you know, if you have different flames and different geometries,
We do not know.
they will be very different.
That's what I would like to encourage you to give us more information. Yeah.
Flames don't align with the flow field. They go wherever they want. They propagate
Sure.
into
Sure,
wave,
yeah.
wave
Sure.
physics.
Sure. Yeah. These are the local principal directions. So
So-
even if it aligns with a different direction, you can always find the local principal directions by doing an eigen.
But I'm just wondering if there's any general relation like the one on the right. If this is what you find for one case, but a flame will go wherever it wants to go. It doesn't align itself. with
Yeah,
anything.
that's right. In the next
Unlike
slide.
unlike a
In the next slide, you will
I
see
see.
that the flame will find it itself
yeah.
to give you that.
Okay. all right.
So I have a question. In fact, we need also to know the time correlation. Is the same time correlation for both cases in direction? Because if it's time,
I don't have that information.
but because even you have this information,
Yeah.
it
But
says nothing about
what we want for this one is the most probable alignment. Then we can average
Yes, I
that.
agree with you.
Yeah.
But for example, you have this picture, but the time correlation is much shorter, for example. So you can't conclude that the flame is I don't know, is seeking. You can't conclude because the correlation may be smaller.
Possibly,
Okay?
possibly. I cannot dispute that
So
because I
it's
don't
not-
have
so
an
it's not-
evidence.
It's not sufficient to show that and tell that.
In the next slide. In the next
Okay.
slide.
But this, so these angles again are the direction between the either largest or smallest eigenvalue, most positive and most negative one,
Yeah,
and the gradient of the Pascal scalar,
that's right.
Yeah.
Reactive scalar.
the reactive.
If it's a flame, it's a reactive scalar. If it's a cold flow, it's a
And
passive.
then the difference between left and right is in and outside the flame, you say?
This is for the cold
Cool,
passive
yeah.
scalar,
Mhm.
and that's for the reactive scalar or in the flame.
Yeah.
And the difference is the most probable alignment of the scalar gradient is with the most excessive strain rate in the
Yes.
flame. And for the classical, the cold flow, it's aligning with the most compressive strain.
And how do you distinguish by simply thresholding? Because it's a
No,
the same quantity, right?
no thresholding. You can calculate this, if you have EHA,
Yes.
you can calculate alpha, beta, gamma
Yes.
by doing a
Yes,
eigen,
sure. Mhm.
thing. And then each one will have a vector associated with it, n alpha, n beta, and then n
Yeah,
gamma.
Sure. Mhm.
And then if you have a del C,
Yes.
then you can also calculate NC.
Yes.
And then all you need to do is take the dot product of
Yeah,
these
but
three.
you need to distinguish between the left and the right. I mean, in cold and warm. So there you need to threshold, I thought.
No, this is from the completely different case. Cold, there are no chemical reactions occurring.
Well,
Cold
that's
flow.
passive scalar. then.
Passive scalar.
Yeah, passive and active. Okay. So-
This is not in a single flame. Even if you do it in a single flame by thresholding,
Yeah.
you will find that.
And what do you think is the reason for that?
It's going to go in the next slide. Yeah. Okay. So let's start with a simple classical picture, where we have these isoscalar surfaces, where we are aligning the unit normal vector with the compressive strain, and then we take this scalar to be the isoscalar to be a flame. What it does is it releases heat, right? So that amount of heat release is measured by the del dot Q, the dilatation, which can be scaled as tau times dA. dA is the Damp-Coulomb number. Tau is the heat release parameter, which is nothing but the temperature rise across the flame. So if the temperature rise is large, the Damp-Coulomb number is very large, that means the red arrow is going to be much larger
Yes.
than the white arrow. Yeah? So then the question comes, who's the strongest to survive this competition? There is a competition between the turbulence and the heat release. So the strongest survives.
And beta in this pitch is just perpendicular to this.
Yeah. So whichever one is strongest is going to survive. That's the, what's his name? The biologist theory.
Or
Yeah.
How big,
Survival of the fittest.
how big is the Mach number here?
Mach number is very low. Yeah. What it matters is
So that
the
is
downwards.
the eigenvalues is approximately 0.
Mach number is 0.00.
So the
Very
sum of all 3 is 0.
It's not 0. It's very, very small.
Close to zero.
Very small. Very small. Okay. Then the compressive strain becomes a extensive strain because there is extensive mechanisms imposed by the flame. Then it becomes an extensive strain. That's how the mechanism is happening. That's a physical mechanism for the change in the alignment factors.
So you, when you were showing these two cases, the cold one,
Yeah.
and so you did exactly what Ashurst and Kerstin did in this paper.
Exactly, yeah. In 1985 paper, I think 87 paper,
Yeah.
Ashurst did, yeah. This result is from the Ashurst DNS one, but there is a lot of experimental experiments done in probably in late 70s or early 80s in UCSD by what's his name? I forgot his name. He's a classical turbulence guy who always interacts with the bachelors.
You mean Kratner?
No, not right now. I'll tell you when it comes to me. I'll tell you.
So that curve is from the DNS, but there is also
From the DNS
there
as
is
well as-
also an experimental.
As well as from the experiment, as well as from the theory. The theory was published by George Batchelor in 1952 in Proceedings of the Royal Society. He made that argument in his theory, and then later on people verified it by experiments and by DNS.
You don't have the alignment with theta here.
Yeah, which is because it's intermediate one, which is not
That's the one
interesting.
which is aligned with vorticity.
Exactly.
Yeah.
But again, it depends what we are trying to address. Here we are trying to address the scalar mixing.
Yeah.
So, after understanding that subtlety in the physics, then how we go about modeling it is we decompose this is a one slice through one of the DNS data we had, and the red line is the flame contours, as you can see. The color corresponds to the progress variable or the normalized temperature. Red means high temperature, blue means low temperature. Okay? And we have flame, very thin flame going all around the domain, and there are some passive mixing situation, or cold region as well as hot region. So for the cold region, we use the classical scaling, and for the hot region, we use the scaling which we found recently, okay, based on the physics, and there is a negative sign in that. The negative sign means the scalar gradients are going to be killed. Okay? And the C3 and C4 are model parameters.
Tau, what does it mean, tau?
Tau is the heat release parameter. Is the temperature rise across the flame,
-1.
or temperature rise divided by the unbound side temperature, or the cold temperature.
And this is the reacting part of the N equation?
This is for the reacting part, yeah.
Of the N
Of the
equation.
turbulent term, that particular term which we were talking about.
That is, del C part of it, del U part of it, del C.
But you wrote dN dt,
Yeah,
and that's what, this is the reacting part of that, is that right?
this is for that term. This term is one of the terms in the dNdt equation.
Okay.
There are other terms which we need to know.
dN dt is just, it tells you, N, isn't N just the reaction rate, basically? If it's the dissipation rate.
We can interpret that. That works
Yeah.
only in the corrugated regime.
So if we say that a high N region is moving along, we're saying basically that's the flame.
Exactly.
And
In the corrugated flames. Yeah.
so this is really, this reacting term is telling you how fast this flame moves.
Yeah, you will see that in a minute. You will see that in a minute. Yeah.
How you obtain this scale?
Which scale?
This
scale?
This, yes. From
Here.
functional reasoning or what?
Here, yeah, physical reasoning. Here. Here the strain rate is given by the flame. That means it's given by the dilatation. In the previous slide we saw the dilatation scales as tau times dA. You can see that there, tau times dA. Okay? And the other things, okay, are scaled with respect to this, the turbulence quantities and the chemical quantity as well. So that's how this whole thing comes out. If you're more interested, I think I would, I have a copy of these papers I can give you if you're interested. Yeah. So then we algebraically simply in a very simplistic manner, we algebraically combine these two to get this overall contribution at a given point. Okay? Then what we do is we collect these type of modeling for these different terms, which I will talk about in the conference. And here I'm trying to emphasize more on the physics. And then in the other talk, I will tell you how we are going about modeling other terms as well. So if we collect those models and then look at the order of magnitude analysis for that n equation, then we can collect the leading order terms, and then based on the leading order terms in the closed form, then we can propose this algebraic expression, very simple algebraic expression for this scalar dissipation rate for the mixing time scale. Okay. And here there are two contributions, as you can see. One, this comes from the pure classical turbulent part, epsilon over k, and this one comes from the thermochemistry or the flame contribution. Under these, you see there are three parameters, C3, C4, and K star. You cannot change them because they are very closely tied to the physical aspect of the problem. And the very specific form we have here for C3 and C4 are here. And why we have it like this is when the Karlovich number is very, very small, you move into the corrugator frame regime. Okay? That means you should not have any contribution from the turbulence. This goes away when Karlovich number is very small. And we have a contribution only from the thermochemistry part. That's what the laminar flame part is.
So this looks very interesting. Is that the first term is more like a flamelet approach, and the second is a distributed reaction term? Is that
that's the idea. That's the idea.
Maybe in a very approximate way.
Yeah, that's the idea. So that the single model can be used across the regime. And that's the reason why we started looking at flames in a different condition in the regime.
How you calculate tau?
Tau is the heat release parameter. If you know the mixture, okay, you know what is the burnt side temperature for that mixture is going to be. So tau is TB, burnt side temperature, minus the cold reactor temperature, divided by the cold temperature.
So it's difference in temperatures.
Exactly, temperature
So,
rise.
so how it normalized to maximum temperature?
It's normalized like this. So it's always greater than 1. Typical value is about 5 to 6.
And how this scaling depends on the noise number?
How it depends?
No, Karlovich number depends.
Exactly. If the Karlovich number is going to change, depending on the Reynolds number for a given large scale conditions, then it will automatically change.
But these coefficients can change if you change.
This Karlovich number is again related to your turbulent parameters because it's a ratio of the turbulent time scale, Kolmogorov turbulent time scale to the chemical time scale. So if you are changing the turbulence, automatically it will respond to it. Okay?
But these coefficients are what?
These coefficients are arrived from the DNS data.
Oh, okay.
And this Kc star, again, once you choose CH4, methane air, or propane air, that gets fixed. Okay? So basically, if you look at this expression, although it looks like we have many parameters to play around with, it's not possible. You cannot change them. There are mainly two parameters, two physical parameters which you can play with in the experiment, for example. One is the turbulent condition. Once you decide, I'm going to have U prime over cell of 6 or 7, and I'm going to use methane air. That's it. Once you decide those two, this equation gets fixed, gets nailed. There is no freedom for you to change anything. Okay? So by looking at this equation, we started comparing with the DNS data here for one of the cases. There are many cases reported in those papers. And the solid line, the thick solid line is the DNS1. And these are the various other models. This is the model we published in 2005, which is far away from it because we didn't take out the subtlety of the physics. Okay, well, once we take out the subtlety of the physics, then it falls down close to the DNS data here. And the classical model predicts 8 times bigger than the classical value. So which I was stating in the beginning that CD varies from 1 to 20. So depending on which value you take, you can get it fixed. But if you're doing a calculation of a flame, you will not know what value to use a priori, unless you have an experimental data for which you are trying to fit your result. Okay?
In classical model, you mean just
The relaxation model. Yeah.
break up.
This model.
Break up model.
Yeah.
times the variance.
But why you present this data in this diagram? Because we can
See, this is the
yeah, why?
going across the flame brush.
Yes, I understand. It means it's universal on it. If you present like that, it's universal.
Whether it's going to vary from one condition to another
Yeah.
condition. We do not know yet, but you will see in a minute.
But why you present like that?
This is a typical way of looking at it. Why we present it like this is,
Yeah.
you see this time scale?
Yes.
That time scale can vary from from one location to another location inside the flame.
No, I speak about that. It's strange because we can, if it's like that, we can tell that scalar dissipation is just function of
See,
variable C.
C.
But it's
Yeah.
not true.
I think that's what will come out here. If you are in the corrugated frame regime, then this one you can replace
Yes.
that with C tilde times 1 minus
Yes, I
C.
agree. But for other cases, it's not.
Other cases, yeah, other cases it may not be true,
But you nevertheless you present like that.
because that's what people like to see.
Okay.
Because it gives you a physical understanding of, physical picture of what's happening inside the flame brush.
But we can go in the wrong direction. This is
Yeah.
the problem.
So this is only a part of the story because we are validating with a very limited data sets. And so can we verify this expression, or can we verify what we have learned using using experimental data? So if you go back to the experimental literature and then look for this quantity, it's not easy to find because this is related to the gradient information, and gradient information is not easy to measure nowadays. Perhaps it may be available in another 10, 15 years, I don't know.
I don't think any of it's very believable because the gradients you're talking about, if the flame is just a little thicker than a laminar flame, right?
It's very, yeah.
0.3 of a millimeter, the gradient will go from, from very high to very low in 0.3 of a millimeter. I guess I don't think one can trust too much. Bob Belger has some good stuff, and Cambridge has some good stuff, but it's just
Yeah, I
starting
agree.
to come out, right?
I agree. We have to take those results with a pinch of caution. Yeah, we agree. And that's why we were thinking what best we can do to validate this learning or to validate this modeling. Can we extend this modeling to calculate some quantities which can be measured in a more reliable way or more with less uncertainties? So there.
So I'm sorry, like one question. I don't understand why, because in my head, Borgit's expression is very similar to this expression.
Very similar to
Very similar to your expression.
which one?
Borgit.
Very similar,
Very
but
similar.
but he does not have this. Okay, that one comes from the dilatation part, the del dot u.
Yes, but you can change the coefficient.
Oh, you can change.
So, for me,
You can change coefficients. I'm not arguing with that. I'm not. Yeah, I don't want to say that word. I didn't want to use that word. You can change, but if you're doing a flame calculation, how do you know what value to choose or what value to pick?
because coefficient is C cut of C4, for example.
Yeah.
We can put everything inside of this coefficient.
If
So-
you have an experimental data for which you are trying to compare, then I agree. If you don't have an experimental data, then so these are the two quantities which we are going to look at in the next few slides. One is the flame speed prediction. Can we extract a flame speed calculation, as Jim was saying a few minutes back, by using this information and then compare it with the measured flame speed data which is available in the literature? And can we also calculate the flame structure from that? So this slide I had it for a reason. I think many of you now know what the flame speed means. It's the rate at which the flame brush is advancing into the unburned side. The Damkoller nearly 70 years, say not 60, 70 years ago, proposed that the ratio of these flame speeds is equal to the ratio of the area change, the terminal flame area by the projected area. A is the projected area as you see there. So for a low turbulence level, we hypothesized that this flame speed ratio is linear with the U prime over SL. And for high turbulence ratio, it goes like a square root of that. And there's a lot of argument in the literature if you go back and look at the literature in that one. And then still this quantity, the ST is the eigenvalue of this problem, which is very difficult to calculate. Perhaps not anymore, as you will see in a minute. So if we use the KPP Kolmogorov-Petrosky-Piskunov analysis, which has been discussed very clearly in Zelovich's book, and the flame speed can be related to the derivative of the reaction rate at the leading edge. Once we know once we can relate the mean reaction rate to the scalar dissipation rate, then we can get this expression using the modeling expression we saw in a couple of slides earlier. Then this becomes a flame speed expression. Then if you use the model in the previous slide for this scalar dissipation rate, then we can get a very simple closed form solution like this. Okay? Where you have these are the model parameters, standard model parameters. We are not choosing any specific values. Whatever people have used in the previous studies, we are taking it. For example, C mu is very well established for 0.05. We use that. Cm is 0.7, again very well established. And these three constants, as you have seen in the previous slide. And here
So you suppose, nevertheless, that this derivative is universal. Because you suppose that scalar dissipation is just function of progress variable. You suppose that?
No.
Yes.
It depends on the scalar, the k and epsilon as well. It depends on the turbulence level.
No, because in this equation you have a just derivative. Okay?
Yeah, and there is a turbulent diffusivity.
Yes, I understand.
Yeah.
But to do this analysis, you need the function scalar dissipation as a progress variable.
Yeah.
So you suppose that it's a universal function.
That is that function which is that function. Yeah.
Is it universal or not?
We don't know. We will find it. We will conclude that whether it's universal or not. We will conclude based on the comparison. I don't want to make any a priori statement in my defense. I want to keep it open. Okay?
But let me ask maybe a strange question. C mu, for example, is it universal constant for any reactions?
C mu is related to the turbulence. It's related to the turbulence.
It's not depends on reactions, just of turbulence.
Yeah, it just comes for the turbulent diffusivity.
Mm-hmm.
Yeah, that's 0.05.
So it's Kolmogorov constant in some sense, if I remember something.
Sorry, what is VT is
Nu T is the turbulent diffusivity, yeah.
Sure.
Which is C mu times k square over epsilon,
Yes.
something like that. Yeah.
And then on the earlier slide you said you modeled this expression derivative.
Yeah, that's right.
What was that looking like?
That is that one.
Okay.
So we can take the derivative of that with respect to C tilde by making an assumption saying that your C tilde can be related to the variance can be related to C tilde. That's what I was saying through this simple expression here.
Yes. And C tilde is rho times C double prime squared, or what is it?
Here.
You mean minus C square equal to this stuff, yes? Minus C square, true. Minus C square. But, I see.
So you suppose that the gradient diffusion for this analysis you need to do.
Yeah, this is a gradient diffusion. I will make a remark about yours.
That's not the case.
About your work, I will make a remark. Yeah.
Okay.
Don't you?
Don't worry.
Yeah, on your next slide, you show this formula. That one. Are you making an assumption about the geometry that you're looking at? Is it a one-dimensional
Yeah,
geometry?
it's a statistically one-dimensional.
Because earlier you have a differential equation for n,
That's right.
and now you have an algebraic equation for burning velocity.
That's right.
In
That's
a more
right.
complicated situation, you use the differential equation,
Exactly.
you wouldn't use it.
No, I wouldn't use it. This is start with a simple one and then move into more complicated. Yeah. Since we are using the KPP theorem, KPP analysis, whatever the assumptions they have made equally applies here. So one of the assumptions was this planar thing. So now we take this expression, and then here the experimental data have reported, once you specify the turbulence level, then your U prime and lambda gets fixed. And once you choose the mixture, then your SL and delta L naught also gets fixed. You cannot change them because those are the thermochemical parameters of the mixture. So if you do a simple analysis of that equation to understand what's really happening, as whether it agrees with Dampfer hypothesis or not, for the carbureted flamelet regime, yes, it does agree with the Dampfer analysis, and the details are in this paper in the CSC 2010, which appeared 2 months ago. So for this carbureted flame regime, we have a linear increase. You can also see in this equation, because Ka is very, very small here, that means this will go away. Okay? This term will drop out, C3 will drop out. C3 has got a 1.5 times root of Ka. So if Ka has become small.
Could you remind what does it mean, C3?
C3 is
1.5 square root of Ka by 1 plus square root of Ka.
So if Ka is very, very small, C3 is very small, so it drops out, and then you could also deduce based on the behavior.
So C3 is very small.
C3 is very small.
When carbureted number
Is very small. Carbureted flame regime, all the contributions comes from the chemistry, from thermochemistry.
If the Carlowitz number goes to infinity, does this flame stop?
That's a good question, Jim. But what this tells you is there is a linear rise. That's what we found. But what Dampler said was there is a square root dependence. That means it's going to level off. So there is a disparity. There is a kind of a difference.
But there is a theory of shocking. No, the theory shows that it's really dependent source.
Exactly. I have that picture. I have that picture, yeah.
In all these considerations, divergence of velocity, fluid velocity is non-zero.
Yes.
Is non-zero.
It's non-zero.
But small. Because Mach is small.
Not small. It's very large.
But density is homogeneous, so
That's right. The
divergence
divergence
is-
comes from the density in homogeneity,
Yeah.
not from the pressure.
yeah. So this is like an elastic approximation. The divergence 0 equals 0.
Yeah. It's,
Okay.
yeah. So now we start comparing that expression with different measurements. And this is the experiment done in 1978 by Fred Goldin at Cornell for a V flame. The flame is stabilized in a rod and the reactants are flowing like this, and they measure the flame speed like this. I trust this data, so that's why I'm using it to compare it with my experiment. And what he has plotted, reported, was U prime over SL versus ST over SL. And these are the measurement points, and these are the various models you see. And the green curve is a model which you saw in the previous slide. And this is a non-repeaters model, which is also very good agreement with the experimental data for this plane, as you see here. Okay. So, what happens if we change another experiment? What happened to my picture here? So this experiment was done at Princeton by Aldrich and his group in 1998. And what they have considered is the flame propagating in a Taylor pipe flow. You have two counter-rotating cylinders, and then the flame is propagating in the cylinder gap between the cylinders. And they have reported again ST over SL versus U prime over SL, okay, for these range of conditions. And the interesting thing which we observed was in the previous slide, previous model was close to the experimental data, but now suddenly it started moving away from the experimental data, as you see here.
What happened? What's the reason?
Wrong constant.
And you have the same constant.
I have same constant.
It's great.
I have same constant. You can make all of these curves to move up if you choose the right constant. But what value of that constant?
And the first experimental data, what geometry?
Is a V flame. And this is the recent 1996 from Kobayashi from Japan for different pressures. As you say, this is 1 atmosphere, 5, 20, and 30 atmospheres, as you see here. And again, they have measured the flame speed, reported the flame speed. You can see them how the agreement is. The green curve is the model we had in the couple of slides ago. Exactly the same constant, no change. Okay. For a very low U prime over SL, this has been done very recently in Queen Mary, and the experiment was done at Bob Shank Lab in Berkeley. And again, they have reported the U prime over SL, the turbulent flame speed for a very, very low U prime over SL, as you can see, because they were interested in Landau-Darius instability. Okay? Whether that becomes important or not. That's the question they were asking in the paper, but they have reported in the one also. And the blue dots are the experimental data, the green dots are from these current model, and these are from the previous models, again with the same constant.
Why do you have so strong fluctuations there in the model, actually?
Good question. It's because the length scales are different.
Uh-huh.
So the model will respond to the change in the length scale as well.
Okay.
It's a Russian data in this one. What we have is, in the previous slides, we were looking at only in this region, and we wanted to see whether what happens when U prime over cell is very, very large. Okay, one of the data I found in the literature was Kalantov and Elaine Shanko data, which was done in 1966, and there are two separate clouds because the experimental was done in a slightly different way. That's why we split it down in a different way. This was with a simple cube, and to increase the turbulence level for this cloud, they used a grid to increase the turbulence level. And that means the length scales will be slightly different for these, and that's why we have these two different clouds in here. This is for that set of cloud, and this curve is for this cloud. If you extend that prediction with the same length scale, then we have a good agreement with the experimental data you see here.
And what nature of this curve? Is it something, some roots?
This bending curve, because in the previous slide I said in the low U prime over a cell, you have a linear dependence, and in the high U prime over a cell, you have a linear dependence again. Okay, because in the high U prime over a cell, turbulent diffusivity controls, and the low U prime over a cell, thermochemistry controls. But in between, both turbulence as well as thermochemistry controls.
I understand. My question is more trivial in some sense. If I try to approximate this curve, is it simple to root from U prime divided by? No,
I don't know. We didn't attempt to do that. Yeah. If you do a square root, then you go back to Damkolov's idea. Yeah. So there is another curve here which was not shown in the previous graphs, which is done by Klimov specifically for this experiment, and then he had a factor of 3.2 in the front with multiplying by U prime over cell for 1 over n. And he was chosen for this experiment, and then that I used. So based on these few slides, what we have concluded, a tentative conclusion is a single expression for the variety of flow and flame configurations without any tunable parameters. We have made that. We were able to make that statement because I think we have understood the mixing physics in the flame, and we were able to write a simple modeling for that mixing physics, which translated into this one. And obviously the KPP analysis involves a lot of assumptions, the corrosion turbulence, thin flame, many things. Two of them I stated here. If you wanted to relax that assumptions, that means we need to do a full-blown calculation. Okay, full-blown either RANS calculation or Leaves, whichever you want. We have chosen the simplest route, which is the RANS calculation. Okay. So now we are going to do a RANS calculation using exactly the same constants, exactly the same model. Okay, using standard K-epsilon closure. The constants which appears in the K-epsilon closure are not tuned. They are very well reported in the literature. We are using exactly those values. Okay, we are not changing any of them.
Swami, I have the question. Nevertheless, it's good fitting, but in fact there are some problem how we define the turbulent velocity.
Yeah.
Okay, for example, in Talantev group, I know it was defined on the leading front. Okay.
Yeah. That's a KPP analysis.
Yes, but if you define the turbulent velocity, because for steady flame it's the same. But if you have the flame which is, I don't know, like in Talantev group, the flame is increasing thickness, okay?
Yeah, I agree.
So you know the difference in the velocities, it's a few of times.
I agree.
So we don't because in your theory it's a real turbulent velocity, consumption velocity.
Yeah, I agree.
In Talantev group, it's not consumption velocity, it's a visual velocity. So maybe Jim knows better this question, this problem.
The measurements, you know?
Yes, because the measurements of velocity is not so easy to do.
I think at these high turbulent burning velocities of 50 or so.
But no, I mean that you know that, for example, Talantev group.
That's the Talantev experiment is like this.
Is yes.
Like this, and there was a 2 plates.
Yes, exactly.
Yeah, 2
so
plates like that.
the thickness of flame is growing.
It's growing, yes. Yeah, I agree.
Yeah.
Yeah, I agree.
So if we define, they define the velocity and the
So the thickness will
This
go
line.
like that.
okay. But if we divide the velocity, for example, on the mean position, for example, where the wireless wave is
I think they have defined it in the leading edge.
yes, it was visible.
Yeah. It's
But
defined
if
in
we
the leading edge.
define, but it's not consumption velocity. It's not in the sense of Dunkerque, okay? It's not the same.
Sure.
So to
Sure. But here, what we have here, the U prime, okay, U prime on this length scale is not up here. That is local. So if you have a U prime and lambda locally for that value, okay, then that is the flame speed you get at that point. So even if there is a variation in the U prime, even if the flame brush thickens, this model should be able to capture, because what we are using is the local U prime, not the upstream value.
it's not consumption velocity, what I want to tell you. It's not consumption velocity.
Fair enough,
Okay? So, and in your theory, it's a consumption velocity.
It's a displacement speed actually. It's a displacement
Yes, but
velocity.
it's done for steady flows. Okay? So, in fact, we can't compare directly visual velocity with consumption velocity. These quantities are different in general case.
I agree with that. In the experiment, it's a statistically stationary experiment.
But we measure
There is a
x. Here is a dependence on the
yeah. There is a dependence on x. I agree.
yeah.
Okay, if you give me a velocity locally, okay, then that's the expression you said. If you give a u prime here because of the change, then you will get it.
It's not the same.
But that's a good point. I don't think you're burning 50 times the mass flow rate
Compared to the
in the turbulent case than in the laminar case. It's not the consumption speed couldn't be 50 times the
This is the displacement speed, which includes
Right. That's to do with,
Yeah.
as Vladimir was saying, it's just a
This
geometry effect.
This is my point.
But still, it's the best data we have at these high.
Yes, I agree.
It's the best data, but it's erroneous to think that you can burn a flame 50 times faster by putting some turbulence into it.
But the
It won't burn
problem,
that much.
how we compare, because this is a problem also.
Yeah.
We can have maybe, because if the velocity of propagation is very quick, what we see, it doesn't mean that we burn with the same velocity.
Fair enough. Yeah.
Uh,
Fair
Do
agreement.
I agree?
Fair agreement. Yeah.
Uh,
Fair point. Not agreement. Fair point. I agree.
It can be here the same.
There.
It can be here in this experiment.
The speed they have reported.
No, if we calculate the volume of burnt gas,
Yeah.
it can be different from velocity measured.
Sure. It can be. It can be.
Okay. We
We agree.
okay.
So now we are going to do some structural information or structural prediction by doing the Rand's calculation. And the flame configurations we take is the statistically propagating flame. In the KPP analysis, there were a lot of assumptions even for the simple configuration. Now we are going to relax it by doing a full-blown calculation, Rand's calculation. And then the other two flames, these are the experimental flames. Why we are not considering this flame is for the experimental case is this is very difficult to stabilize in a real experiment for a statistically dependent flame. It's inherently unstable or unsteady. So there is no data which I am aware of for that configuration. But there are a lot of data. The V flame data is there are quite a lot of V flame data available. I have chosen only one for this for today. And for turbine pilot, this one is done by Naga Peters. There are 3 different flame conditions. I will try to show all 3 of them in this presentation. So statistically, flame, just a configuration to show how it propagates. Okay, this we start with the initial planar flame or products, and then we're just going to advance in time, and then we track that using K, epsilon, by solving all the equations in a coupled manner. And the V flame calculation again, it's just in the flame is stabilized in the rod, and then the CH4 at 0.6, the equivalence ratio 0.6 is going up, and you have a flame brush which is sitting there, and we calculate in that domain of that size, and this is a typical grid we have, and that the U flame over SL for this flame is around 2.1, which is not very high. And this experiment is done in France by this group. And the turbulent Bunsen flame, pilot stabilized Bunsen flame, is done in Aachen by Norbert Peters group, which was published in CNF in 1996 for these 3 different conditions, and we are going to see some results for all of them. Okay? And in terms of the combustion conditions, I'll come back to this in a minute. Okay, I'll come back to that later. So how we are going to model this, model these flames is, we start with this progress variable equation, mean progress variable equation, and we want to close this mean reaction rate, and we also solve the variance equation, okay, because variance appears in the mean reaction rate expression according to this model. And then the standard practice is this way, where you have this state space variation, where you calculate planar flame, laminar planar flame, and then tabulate these values based on the progress variable, and then by pursuing a PDF, which you can pursue, for example, a beta PDF or some other form, for a given mean comes from this equation, and a given variance coming from the variance equation. Then you can calculate this mean by integrating with the PDF.
So here C is the number density?
No, C is a normalized temperature,
Yeah.
which is called the progress variable, or a normalized mass fraction. And in FSD approach, the flame surface density approach, the mean reaction rate, you can do it this way, in a simple way. The difference between this approach and the standard practice, this is called the FPA or a flamelet approach, here is the factor I naught here. Okay? What this model assumes is the turbulence does not do anything to the flame. The turbulence locally propagates as a laminar flame. That's what this model does. But in this model, we have this I naught factor, that I naught accounts for the effect of the turbulence strain on the flame. Okay? And that is I naught. So this could be seen as a strained flame, the effect of a turbulence strain acting on the flame surface. And we can write a transport equation for that, or use algebraic model. There are many approaches in the literature if you are interested in. Here I'm just trying to give you a gist of this approach which are available. And there is another approach done by Derek Bradley at Leeds. The mean reaction rate is integrated twice. One is with respect to the progress variable. Another one is with respect to the free dynamic strain exerted by the turbulence. Okay? And if you assume the joint PDF to be independent, okay, then you can express the joint PDF with the product of the 2 marginal PDFs. Then you can simplify and come back to this from here with the factor PB, which is calls as the probability for burning, and Bradley has a number of correlations for a given mixture, for a given turbulent conditions, various things. So once you can use the correlations to calculate the mean reaction in this approach.
This kappa, okay, what is it?
Kappa is the turbulent strain, yeah, or stretch rate.
And zeta?
Zeta is the progress variable. It's a sample space variable for C.
So something proportional to C or
Sample space variable for C, not proportional. So what we are going to do is we are going to use the scalar dissipation rate to quantify the stretch, okay, in this approach, because dissipation rate is linked to the gradient information. So if there is a turbulence straining, the gradient is going to change. Even if there is a curvature because of the turbulence, the gradient is going to change. So if there is a stretch, means you are straining as well as bending the flame. The combined effect of those two things is called stretch. So the stretch effect can be very well reflected in the scalar dissipation rate, which is what we are hoping.
And what actually C in tilde, maybe still it's a question. It is not average, it's something really...
It's a favor average, density weighted average. So the way we approach this problem is the mean reaction rate, again integrated twice. One is the progress variable, psi is the sample space variable for n, for this dissipation rate, for the scalar dissipation rate. Okay? And then we do not assume the joint PDF, we do not assume them to be statistically independent, the progress variable and its gradient. We express the joint PDF using Bayes' theorem. So you can express them as a conditional probability multiplied by the margin of PDF. Okay, we are not making any assumption between the step, we are just using the mathematics, the statistical mathematics, so which comes out to be in a very simplistic form like this. So basically, if we know this quantity, then we can calculate the mean reaction rate by knowing the mean C and then its variance, because we presume a shape for the PDF, for that PDF, okay? That means we can calculate the mean actually. And what we do is we calculate this PDF by taking to be a log normal PDF. The reason behind that is these reaction layers are very thin layers distributed in the flow. Okay? These are less space filling. So whenever you have a physical process which are less space filling, a log normal PDF is a typically good approximation.
And you use such variables, just equations have more simple form, or why use such kind of variable, new variable, zeta and psi?
Zeta is the sample space variable.
Yeah.
Like this, we have to go to the statistical theory to explain that statistical thing. In a very simplistic manner, you have a probe, for example, which measures temperature, okay, which is going to go like this. Okay, and you do many realization of that. Another experiment, maybe which will go like this. And then the sample space variable, what that means is, I'm going to take particular value of t, which is equal to say t star, which is t star. And then you collect all the points on the point, and then construct it. If we use a log normal PDF, then we need to know the mean to calculate the log normal shape. And the mean comes from this epsilon sub c model, which we have seen some few slides ago. And then f of c is a very nice simple function, which you will see in the next slide. How it comes about is from a number of lambda flame calculation. Again, once you fix your mixture, f gets fixed. You cannot change this one. And this equality, it should be equal here actually. This equality comes from a simple identity like where you have the mean dissipation rate is nothing but the conditional dissipation rate multiplied by the PDF. Okay. That's a statistical identity. This expression comes from that by simple algebraic calculation. So the f of c is here. This is for the methane air case for 0.6. This is for methane air for stoichiometric, and this is for propane air. Again, you could see that f of c is very well collapsing for different strain rate, for different. This calculation was done in a post-flame calculation, and for different strain rates, you have a very nice collapse in this region. Right? That's where the chemical activities are going to happen. In this region, it's a thermal diffusion region. It's a preheat region, so which can be calculated in the calculations. So we use this information to close the reaction rate. In the same form, we can also calculate the mean species values, either major species as well as minor species in this form, okay, where you simply have the flame rate value, tabulated values from that, and then by integrating over the PDF, you get this mean value. So the flame conditions we consider for the planar flame are two different conditions. One is along the line, Ka equal to 1, 9, and another case along this Ka equal to 6. I think it's over 6 or 7 along those lines. These are the number of points we consider. These are the number of flames actually we compute using this approach. And for the experimental flames, as you see, one is in the corrugated flame, another one is well into the thin reaction source regime. Okay? We are going to use exactly the same model parameters without having to change any of the constants for K epsilon as well as for the combustion submodel. So if you analyze the planar flame results, then again we can extract the displacement speed for the leading edge, and then the data points are the cloud compiled by Derek Bradley in his Proceedings of Royal Society paper in '86. And this solid line is the KPP expression which we saw in a couple of slides ago, the long expression, closed form solution. That's a solid line. And if you use this simple reaction rate model where we had omega dot bar equal to 2 over 2 Cm minus 1 rho bar epsilon sub c, along with the transport equations, then that is the dotted line you have. So you have a change, and the difference between that solid line and the dotted line is the solid line assumes the turbulence to be frozen. The turbulence is not spatially varying, but in reality the turbulence can decay in space. So that variation makes that difference, the shift in the flame speed. And the other symbol here, the UF, is the unstrained laminar flamelet. That's the standard approach everybody is using in the literature. That is that curve, which does not account for the effect of the free dynamic strain on the flame. Okay?
And what's the horizontal coordinate?
This is U prime over SL.
U prime
Over SL. Yeah. Laminar burning velocity. And then this one is the unstrained, the strained flamelet model, the bottom one, okay, as you see here. So this is for K equal to 1, and this is for K equal to 6.4. This is, I don't know whether you call it as a corrugated flame or a distribution regime. So it's an open question. If we classify these flames based on Peters criteria, then this is in the border of the corrugated flamelet regime to the thin reaction zones regime, and this one is in the in the thin reaction zones regime. Okay. And they're using the accounting for the strain effect where the dissipation rate, where the mixing physics clearly shifts the curves into the experimental cloud very nicely, as you can see there. So the B flame sample results, again, as you can see here, these are the experimental data point. It measured for the normalized temperature. This is for the unstrained flame model, and this is for the strained flame model. They are equally good. Both of them are equally good because U prime over SL is 2.4. That's in the corrugated flame regime. So corrugated flame regime, you would expect the laminar flame, the flame to be a locally laminar flame without being disturbed by the turbulence. If you use that idea, then it works very well. See, the more complicated flame is the Bunsen flame. What we have here is the unstrained flame, the reaction rate time scale, as you can see here, as computed using unstrained flamelet model and the strained flamelet model. If you use the unstrained flamelet model, you are burning too quickly. Okay? Because you assume locally the flame is a laminar flame and it's consumed at that speed. But if you allow the strain to affect, if you allow the turbulence to impart the strain effect on the flame or the burning, then the flame gets longer. And that length is comparable to the experimentally observed values, which are all reported in the paper, which you can download from the university and flame website. And these are the typical comparisons for the mean velocity and mean kinetic energy as computed. Here what we see is a normalized temperature. In the previous slide I made a statement that the unstrained flamelet is burning too quickly. That means the temperature in the centerline will rise very quickly. Okay, as you can see, these are the experimental data, okay, as you see here, and these are the strained flame calculation data, and these are the unstrained flame model, unstrained flamelet model, as you can see. So by 10.5, XOD equal to 10.5, unstrained flamelet model tells that you have completely burnt the fuel in the centerline. But the experiment says, no, you haven't burnt it, there is still something left. That's the difference. Similar thing you can see in the mean mass fraction value. Since you have completely burnt the fuel in the centerline, okay, you have very close to zero value at that point in the CH4 value. And these three columns are for, this is for F1, flame F1, which is very close to the thin reaction zones regime. This is for F2, this is for F3, is close to the corrugated flame regime. So the damper number decreases as you go from here to here. Okay? So the same model is used for this range of values as well. So we can go on and on, but I think I would like to make one final point for the CO comparison. What we have is the R over D versus the CO mass fraction measured in the experiment, and these are the values computed using the strained flamelet model. That's the model we have been discussing, and this is a G equation model. I didn't compute that, I just took the value from the literature computed by someone else for the same flame. And this is the joint PDF, transported joint PDF, again computed by Peter Lindsay in Imperial. So I took his value and compared it here. So you could again say they are equally good or equally bad for CO. So to conclude, I added these 2 points last night because I thought what we are trying to do is turbulent premix flames, which which is a very good candidate for lean green combustion, as you can see, because it emits less amount of pollution. But there are a lot of modeling challenges because this lean flame is very unstable, as everybody knows, in the practical conditions. So innovative solutions can be found economically. What I mean by is running simpler simulations using K-epsilon or a RANS approach rather than DNS or LES for a practical geometry. Okay? So economical solutions can be found quickly if submodels are made more reliable by putting a lot of emphasis on the physics. By learning about the physics, that's where the DNS and laser diagnostics are very, very helpful, and we have to rely on them to understand the physical picture, what is in this world. So I have tried to convince you that there is a reliability and accuracy for the physics-based modeling approach is demonstrated by showing these various comparisons. Okay?
Yes, since you mentioned this PM combustion, and I think about application to, for example, hydrogen-rich lean flames. Those are very special flame in one sense because they are the two-well flame speed is affected by local enrichment at the domes of this flame. Would your model? I didn't see in your model something that could take into account this.
The differential diffusion.
Yes.
Yeah.
That is buried into the flame net calculation. So it doesn't appear at that level. So we haven't applied it for hydrogen flame, so I cannot make any...
Yeah, in fact, my second question was, so you haven't tested or compared the model to very lean hydrogen
Not yet.
frames?
Not yet, yeah, not yet. Yeah. So the ongoing activity is we want to understand and improve the CO predictions. Either it's a chemical kinetic effect or there is something else happening. I don't know yet. So the application of this modeling to LES is another ongoing PhD, which is also an open question. And then application to combustion instability calculation is an existing PhD topic. I don't think that's the right for this audience. So the activities on the pollutant emissions and predictions and noise predictions are evolving exercise in our lab because these are very important issues in terms of environments and also economics, in terms of economics of power generation. Okay? And the use of these models for the practical combustors are being explored in various gas turbine manufacturers as we speak. They're trying to find these models for the generator. And that's where I would like to stop and then take any questions, and then just to conclude, that's my statement.
Let's first thank the speaker then.
Do you have data about flame from velocity versus non-cooling number?
You can construct it based on these reported values, yeah. Yeah. You can construct that.
Yeah, and what is the dependence, typical dependence?
I can't remember, but there is a paper in 1990 by Ken Bray in Proceedings of Royal Society where he has derived and clearly noted that expression what you are asking for.
We know that premix flames are different from non-premix flames because they're waves. They propagate normal to themselves. Huygens principle applies, and all of this. And the G equation accounts for that. Flame surface density model, at least it assumes that there's a surface and there's a certain reaction going on per unit area of that wrinkled surface. But I think your approach, I don't see anything that has anything to do with waves. I don't see any propagation.
This is a statistical approach.
Yeah, so, I mean, are you really saying that a non-premix and a premix flame are the same, except the way you model the reaction rate is different, basically?
Yeah, basically.
And,
the mixing physics is different.
I'm just wondering, do we know, I mean, it's obviously more efficient to do it this way, but which of these three approaches is going to win out in the long run? I don't know.
I don't know.
I'm not sure you'd have to follow the details of
Yeah.
the wave structure. What you're doing is, you don't
It's
care how
nothing.
it gets there,
Yeah.
you just statistically
That's right, yeah.
analyze
Since you have raised that point, just for comparison purpose, this approach takes 3 hours to compute the results which have been shown for Bunsen
it.
flame,
Yeah,
3 to 4 hours on a desktop.
yeah.
G equation takes 2 to 3 days because you need to reinitialize. Joint PDF approach, a week or 1.5 weeks.
And you may not need to know all the wrinkled structure
You
of
may
the
not
wave
need to.
get the right answer.
You may not need to.
I just want to comment G equation because we did the G equation runs calculations. It should be on the same competition effort as your method. I don't understand why it takes 10 times more.
That's the number I got from Hellman's paper.
Okay.
We didn't do it.
They probably you shouldn't compare that. I think they are on the same competition.
Possibly. We didn't do the calculation. I clearly noted that.
I have a question. You compare CO in simulation.
Yeah.
How these chemistries come in through the reaction rates or CO?
No, the chemistry comes in through this,
Wait.
through this.
Okay, this is like.
So you can do this in a,
It's like flame at
yeah,
in
exactly.
summer average.
Yeah. So you can do a counterflow flame, and again your CO can depend on what canonical configuration you use. The configuration we used is a product to reactant that we believe it's more likely, and there is a paper arguing that by Libby and Williams in the 80s.
I have another question. This is clear for me. How your flame speed formulation comes into this model?
Flame speed formation doesn't come in here.
Okay, it's separate.
Yeah, it's a separate thing. Yeah.
Okay.
I wanted to show that the same model can be applied to predict the flame speed and also the flame structure without having to play around with the model parameters. I think people who does the modeling knows the art of the work, how much they have to play around to get the numbers right. But here I'm trying to show that it may not be necessary if we have a good understanding of the physical processes.
Could you summarize again Mr. final conclusion? What exactly is your interpretation of what makes the difference between the different alignments with alpha, with the largest and smallest eigenvector
I think let's go back to
in
this.
different cases? Yes.
So that's very well known for a passive scalar situation. Right? So we have a normal vector n which aligns with the gamma compressive strain, and then now we take these green lines to be a flame. Once you have a flame, then it's going to release heat,
Yes.
and that heat release is going to create del dot u, non-zero del dot u,
Yes. Okay.
and that's del dot u, which will go like the heat release parameter tau times the damper number dA. So if you have a that dA is a local damper number. It's not usually traditionally treated to be the upstream damper number. So this is a local damper number. If the local damper number is large, then you have a very large heat release rate. Then there is a competition between the white arrow and the red arrow. So one is trying to push it, another one is trying to pull it. So whichever one is stronger is going to win. And that's the real mechanism, which makes it different. So.
Yeah. Okay. Thanks.
If you energy release, this formula describes situation with fluctuations. Suppose fluctuations very weak, close to laminar regime. We should know, for me it's plausible to add some, how to say, laminar-like source. Why you haven't automatically in your approach?
Are you asking whether this formulation will fall back to the laminar situation when you have...
Yeah, it should be some, how to say, joint equation of how to say, which take into account.
That will come from your transport equation itself, right?
But it's
Some averaging, very specific. If you draw, say, some time derivative and say that we've got competition between source and diffusion, and just diffusion important. But of course it's true, but what?
In a laminar flame, we don't have that, do we?
In laminar flame, you get right.
We don't have that.
But nevertheless, you've got equation for, say, progress variable, which average, and we can step by step reduce turbulence. And we should back somehow for laminar
So if you reduce step by step,
yeah.
then the averaging does not make sense. You don't need to average it.
No, it's not true. You can average even your velocity tensor. Formula will be just constant, nothing else.
But all scalings cannot be there.
I think we should continue the discussion all the time, because we have also another presentation. So, are there some very quick questions?
Maybe small question.
Okay.
Swami, I don't understand, because you use this equation for divergence of velocity for all lengths or all the thickness of the flame.
This is the scaling argument.
Yeah, because in fact we have this the change of divergence at each is a scalar surfaces.
Yeah, it can be different from one scalar to another scalar.
For me, it's a maximum.
It's a very simplistic view. I agree.
Yeah, because
I agree. And this one, if you put a thickness around it,
yes, it's zero.
then this can be different.
Practically every is zero. Okay, it's small. It's always interlevel.
Sure. But here we have taken that to be a very thin interface. An interface with a heavy activity.
I think we have to close this presentation and let's thank the speaker again. Short break.
Yeah.